I'm going to do an estimate. The estimate that I'm going to do today, and I still have to assign estimates for the next few days. The estimate I'm going to do today is for something that should surprise you by the way I describe it. That is, what's the color of a black hole? What is the color of a black hole? One would say black, it's a black hole. And one would say, well, if there's things around the black hole that fall into the black hole, maybe they emit, but I'm not speaking about the color of things falling into the black hole. I'm speaking about the color of the black hole. I don't know if you catch what I'm referring to. I'm referring to the fact that because of quantum effects, black hole emits thermal radiation. The thermal radiation has a temperature, and if the temperature is sufficiently high, like the sun, 6,000 Kelvin, the sun is white. Astronomers would say it's green in the sense that the dominant wavelength is green, the peak. But we say it's white. So if you have a black hole, a temperature of 6,000 Kelvin, like the sun, it would be white. It would look white. And so the estimate that I want to do is like how big should a black hole be to look white, to be white. Okay? That allows me to introduce one notion. And again, it's an estimate, it's not a derivation. Yes.
Quick question from before. You said the seminars, the quantum gravity seminars, Tuesday at 10?
Yes. Yes, these are the look quantum gravity seminars. So they are generally quantum gravity. We meet every week. 1 week is international, 1 week is local. There's a schedule. You're welcome to join anytime.
Can I write it on IGC website?
It's not advertised, but we are in Whitmore at 3:10. I'm gonna send a message about the event next week.
Okay.
And then you can join anytime. Okay, the one on next week is on black holes. Okay, so let me try. Should respect the rules. Respect the rules. Event time. So the color of a black hole. So the first thing that you need to know is that the black hole has a temperature because of quantum effects. Quantum effects are linear in h-bar. And you can get something in dimensions of a temperature. This is the OT temperature, h-bar over m. I want a temperature that is like the temperature of the sun, that is 6,000 Kelvin. And I don't work with temperatures, I work with energies. I know KT in a room here. T in a room is 300 Kelvin. But I need a KT because I don't want to remember Boltzmann constant. That's not something to do. So this, I hope you know by now, I remember it in electron volts, 1/40. And T sun is 20 times room temperature, 20 room, and so it means that KT sun is 0.5 electron volts, which makes very much sense. Okay, so that's the scale electron volts. Now I'm asking, what's the mass of a black hole of the same color of the sun? A white black hole. A white-looking black hole. So I just have to invert this one. So it's m 1/t. I'm gonna put here kT, so that it's energy. Here I put the Planck energy or Planck mass, and it's a mass. And dimensions are fixed. In case you don't know, mp(c squared) is 10 to the 19 GeV, and mp is 10 micrograms, is 10 to the -8 kilograms. So here I use 10 to the 19 GeV over EV. Here I put 10 micrograms of 10 to the -8 kilograms. This is 10 to the 9, 10 to the 28, -8, 10 to the 20. Kilograms. 10 to the 20 kilograms is a number that doesn't tell me much. I don't know how big is it, but I know the density of water. 1 meter cube is 10 to the 3 kilograms. And so this I can certainly write as raw water. And here I get a 10 to the 17 meter cubed, which I can write as a 10 to the 5 meters is 100 kilometers. There's a factor 2, maybe 200 kilometers cubed. So a cube, 200 kilometers. Was precise. So that's how big this black hole is. And if you don't want to think of water, think of rock. Rock has the same density as water, factor of 3. Now, we are not tracking factors of 3. And so go 200 kilometers, also 200 kilometers down. And you make a black hole out of that. And that would be a 6 color as the sun. All right? Questions? We have talked about it. Black hole can be wide. Questions?
What would be the wavelength?
Say it again?
The wavelength.
600 nanometers. Like typical in the middle grid and Planck spectrum. So like the sun has. There's another question should come up. Yes.
Is this like would this black hole be, like, how would that compare to like the size of the black hole?
Yeah, so 10 to the 20 kilograms is like moon-type range, like, I don't know, like out from side to side, 200 kilometers. So, so if you're not, say small, like, and so, so if the question is, what's the color of a solar mass black hole, a 30 solar mass black hole that we see everywhere? It's black. It's black because you can compute this temperature, you can compute the wavelength, and you see that the number that you get, the temperature is so low that it's covered by many other effects that are way more important than this one. And so you should just ignore this effect. Like saying that a solar mass black hole has a temperature, it's a pen and paper statement that doesn't correspond to anything in nature in the same way as saying that you balance a pen on the tip and you compute the uncertainty relations for the pen. The uncertainty relations are not the relevant physics. There's practical things that come first.
Yes. So I guess just, is there an intuition for why temperature would be inversely proportional to mass? And with the quantum effects, because that's kind of the opposite of what I'm expecting. Like, yeah, you get more matter, yeah, like it's a lot, right? And why would it be inverse?
You're catching something important. It's fair to ask every time you see a quantum effect to ask if there's a classical version of that. So what you're noticing is that while for water, if I do work on it, I add energy, the temperature increases. To a black hole, if I add mass, if I add energy, the temperature decreases. You put in energy and you cool it down. This thing has a name, but how the energy changes with the temperature is called heat capacity. And for most standard bodies, it's positive. You add energy, you increase the temperature. And for black holes, one would say, oh, these are weird. You add energy and you decrease the temperature. It's not black holes that are weird. It's gravity. Like, if you have a planet around the sun and you put in energy, you're not going to send it closer to the sun. You're going to send it farther away. It's going to have lower velocity. If you have a cloud, you put energy in the cloud expands and cools down. Self-gravitating system have a negative capacity. Self-gravitating system has this property. You put in energy, and you can ask if you can prove it quickly, pen and paper, and when you're done it for the harmonic oscillator, you put in energy, the temperature raises. Is that because when you put in energy, the average kinetic energy and the average potential energy are equal? Period theorem. And so if you put total energy, you also are increasing the kinetic energy, which is temperature. Okay? But if you have a potential that is 1 over r minus 1 over r, you can do again the calculation of the BVR theorem, and you find you put in energy, and you're increasing the potential way more than the kinetic term. In fact, the kinetic term is going down. There's a minus sign there. So this is a property of long-range attractive forces, and gravity is a long-range attractive force.
Would this be the equation of state of the system?
You can think of it as the equation of state of the system, even though for gravity we don't think of it as equation of state, we think of it as dynamics. Yes.
Can you explain again what MP over GT is?
Yes. So I follow this logic when I do estimates. I say I know general relativity and I know special relativity, but I want to track what are quantum effects. This is a quantum effect. So I first identify where each bar appears. So leading order quantum effect, so should be linear in each bar. Okay. So that is if there's no quantum phenomenon, temperature is 0. So I put an H bar here. And then I can either do dimensional analysis or know the derivation. And out of that, say temperature, it has dimensions of energy, H bar over M. Okay? If you want, H bar C is energy times length, and MC squared is an energy, and that gives you the number. I said it wrong. H bar C is energy times length, and here there's a GM, which is a length. And so if you want, it's H bar C over Schwarzschild radius, okay, which gives you a temperature. Then I want, this is for logic to get the formula. Then I want a number. And for a number, I want to be able to compute ratios of things that are dimensionless times things that are the correct dimensions. Okay? And so first I'm writing M equal 1 over T. I forget the H bar, and that's it. If T is 1 over M, then M is 1 over T. And then I feed everything back because I say, this is M has to be proportional to some mass, Planck mass. And what is left is something that I have to build out of H bar. And this Planck mass contains a square root of H bar. So here it has to be mass over mass. I'm going to need a K. And so now these ones are things that I remember because this is 10 micrograms. This one I can think of it as an energy with a C squared, and it's 10 to the 19 GeV. So in this way, I've blocked the formula in a way where I can go estimate quickly. Okay? And so just to say it once more, to me, this is theory, this is estimate. This is the physics ingredient, and this is the way I do the estimate. And you see an H bar. If you go check the formula for mass Planck, it's square root of H bar. There's a square root here, a square root here that gives back this H bar. Okay.
Why would KT be in the unit of mass?
Oh, so T has weird units, MP, but KT has dimensions of energy. And I'm playing with C, like everything that is massive and multiplied by C squared becomes energy. Okay? And so, yeah, if I wanted, I could have, yeah, Planck energy instead of Planck mass. Okay? In fact, it's what I'm doing, no? I'm saying mass Planck, but here I put kilograms and here I put GeV. Yes.
I think I missed what M was. Is that,
Mass of the black hole.
oh, the mass of the,
Yes. Yes.
in general? Like, I guess for the 6,000 Kelvin.
So this would be the mass of uncharged, non-rotating black hole that emits radiation that is thermal at this temperature.
Okay.
No?
This might be. Is the radiation predominantly EM for this type of black hole radiation?
Yeah, so it's going to be electromagnetic and gravitation. And everything else is suppressed because everything else has a mass. Yeah. Good. There's another question you should ask. We're going to address it another time. That is it bright like the sun? Say it has the color of the sun. But can you warm things? Can you put a solar panel? What's the power? That's what I'm asking. We're going to estimate the power another time. If you estimate the power, you find it's a milliwatt. It's just okay for an LED. It's not, this is gonna irradiate for a very, very long time. Okay? Why did I do this, even though most of what we are gonna do is classical? We're gonna do horizons, laws of horizons, area law for the horizon. All of the language, all of the intuition comes from entropy. To speak about entropy, you need a temperature. Better to tell you about the temperature from the beginning in the most concrete way. How do you make a green black hole? Okay, that's a green black hole. Just so that I convince you it's a green black hole. Let me see if I have it. I'm not going to show you a green black hole, but I can show you. Yes, showing you this, no? 6,000 Kelvin. This is green, no? That's all I wanted to show you. Good. Okay, so plan. We really have to discuss horizons. And it's the kind of topic where there's a number of notions of horizons that range from like very special, work only in some very special cases, to more general and dynamical, and we have to go through all of them. Yes.
What should we sign up for, or do you estimates for this?
You can already sign up. And I haven't put the topics yet. I'm sorry. It's okay. I'm gonna put the topics. I'm gonna say already the topic for next time. Estimate power radiated by the sun. Okay, that's gonna be a useful one. Estimate the power radiated by the sun, knowing that you get a kilowatt per meter square at the Earth distance. We get a number, then when we do black hole mergers, we know that number, and we can ask black hole mergers how many suns is it. Okay? It's gonna be the other estimate. Thank you for reminding me. Okay, so I'm gonna go through a list of notions. In principle, it's okay if we cover the first three and we do the next two next time. So feel free to ask questions. I don't want to rush it because there's a lot of material, as you can see from these references. And I'm going to tell you which one is more helpful, but I collected all the ones that I do find helpful. And there is one that if you don't know of, I think it's useful one to look up. Garrosh has a book on general relativity. It's a booklet, small, with like 20 chapters or 2 pages each, where things are explained like sharply and quickly, just to the point. It's some of the style that you find in Wald's book, but lighter. Okay, so let's start. First thing that I have to tell you is how to define event horizons. This is one notion of horizons. Don't take the word event as just like it's part of the definition. We are going to do horizons that are not event horizons later. So I first have to tell you about this older notion of event horizons and how they are related to this notion of last light ray. So this is a causal definition. You can really think of it as a causal definition of a black hole. You say a black hole is a region of space-time that traps stuff forever. And forever is key here. What is the event horizon? Is the boundary of that region. So there's a few assumptions that are technical, and that's where Don Penrose diagrams, I can describe it. To say that they trap things forever, you have to have a notion of things not being trapped. And so, for instance, light that can escape to infinity, light that escapes to infinity escapes to future null infinity. And so now you say, well, light can escape, but cannot always escape. There's some light that remains trapped forever in the sense that tends into a curvature singularity. The boundary between the two is the event horizon. And what's inside the event horizon, you call it a black hole. That's clean, sharp mathematical definition. And once we give the definition, then we can complain and ask if this is physically relevant or just mathematically good for proving theorems. Okay? You can write it in a formula. It's a weird looking formula, but it's just what I said. You say, look at where light can go. Look at the past of where light can go. Look at the boundary of the past. And that's the event horizon. That's the way you find it defined in the literature. It's the same statement that I have here. There's a region that traps stuff forever. What's the boundary of that region? But you want to be careful in the sense of defining it in terms of light. Okay? Now, here is the caveat. It's this statement that this notion is teleological. What does teleological mean? This is like one of those notions that in philosophy Aristotle's liked of this distinguishing causes from final causes. We'll always speak about causes. Something produces something else. And this is not something that is produced. This is something defined by check what's the last ray that can come out. Once you find the last one, then that's the boundary. So you're not gonna know until you find the last. But you will never know if it's the last, because maybe the day after there's another one that comes. So you have to wait the end of time to find where the horizon is. This is what people call teleological. You have to go far away to the infinite future to make sense of something that happens today. It's a final boundary condition. One would say this is not physical. To be physical, you have to be able to go there and check. You cannot go there and check. It is useful to prove theorems. You know, the horizon of a black hole has an area that increases. Well, this one increases because it's defined so that it can only increase. And then you can prove results. The criticism is that it's less useful, for instance, in numerical relativity, in physical situations where you want to say there's a black hole there, and this tells you, well, you have to wait the end of time to tell if there's a black hole there or not. Because what if stuff gets trapped for 15 billion years and then they come out? Then it's not a black hole, because the black hole is defined by something where nothing ever comes out. No? And so at some point there were people claiming black holes don't exist. Don't exist in the sense that we don't know if things come out at some point. But we still call them black holes because they have all the physical properties of them. And so this is a fair criticism. If you want to speak about physics of things, you don't have to wait the end of times. In quantum gravity, where one asks about black hole evaporation, black hole emits radiation, so it loses mass, so it gets smaller. And so it could disappear at some point. Is it going to trap things forever or release things once you get to this point where we don't know the physics yet? Does the definition rely on physics that we don't know yet? That will make it a definition is used for only mathematical relativity and not as a physical law. Okay? This notion, teleological, or the word that I like to use is last ray. You have to check at the very end. The last ray that comes out, that's the one that tells you that there's an horizon. The word that everybody uses is event horizon. And you see, not people say not horizon, but event horizon, they refer to this notion. Okay? Are there comments on this? Yes.
Is boundary feeling spatial?
Okay, so good. What kind of boundary is it? So if you take a spatial section, you're going to intersect it somewhere. So you would say it's a place. It's just that you don't know if this place is here or not, because you would have to wait the end of time to know if it's there or not. First remark. Second remark, you could track this point. So at one given time, it's a two-dimensional surface. But if you follow it, by definition, this being the last ray, then it's null. And so it's a three-dimensional object that is spheres times a null direction. Okay? And so if one says, why is it null? Well, it's null by definition. It's the last ray. Okay? Okay, so let me try to introduce a notion that is more physical. A notion you can use when you're doing a numerical simulation, and you're at one given time, you ask, is there an horizon there or not? A notion that you can use when you say, whoa, there's this merger of two black holes. Before merging, there was a black hole and another black hole. What was the size or the horizon of one of the two black holes? Yeah. So this goes under the class of things that people call with various names. And I'm going to describe one specific one, the notion of trapping horizon, in the sense that it traps light instantaneously. Not forever, but it's a local notion. And the full theory of these things, you find them in these lecture notes that are a GR2 course of a few years ago that was all on this topic. So it takes a while to absorb it. I'm going to try to capture just what we need. And how I'm going to do it, I'm going to do a huge simplification. Instead of treating it in full general relativity, I'm going to assume spherical symmetry. No, black holes don't have to have spherical symmetry. Black holes can form from merger, and so there's this phase that is not spherically symmetric. Eventually, they're going to have a spin. I'm going to simplify tremendously by just saying, let's assume that we have a spherically symmetric spacetime. Any spherically symmetric spacetime can be written as unit sphere times something r squared that we know it tells us the area of the sphere. And then you have two directions that are left. If you want r and t, it's better to work with double null coordinates because we are going to ask causal questions, or we're going to ask about light. So u and v, as we have already done. And then we have two unknown functions, or two functions that define your spacetime. So this u dv is double null, or light in going in and light going out. And these two functions are the ones to determine a spacetime. And of this one, we have the interpretation. The interpretation is area of spheres. Okay? And of this one, we have to think. It has to do with redshift. Okay? You send in light, how does it come out? With what redshift it comes out? So this I've said, area of spheres. Now, let me introduce two vectors that you can think of as take a sphere at a certain time and shine light going out. That's going to give this cone going out. What's the tangent vector? Well, direction is dv. I'm going to normalize it so that I put in this alpha, and I'm going to call this vector L mu. And then I can also shine light inside. If I shine light inside, I'm going to call that n. And this at some point is going to cross. Okay? If it was flat space. Let me say it again. This thing is what would happen in Minkowski space. You take this sphere, you shine light out, it goes away, you shine light inside, and it's going to reach a center. The question is, what happens in a more general spherically symmetric spacetime? And so let me introduce two notions that are important. The first notion is, here you have an area of the sphere, and you can say, suppose that I follow the sphere when I go out. This area is going to increase. What's the logarithmic rate of increase going out? So logarithmic rate is derivative of the logarithm of area. You see that by construction, you get something dimensionless, because this element defined dimensionless. And this quantity is the expansion. Expansion going out. And then you can also define the other one that is going in. This is going to contract, so you would say this is negative. You still call it expansion, then you say that it's negative. Okay? Defined in the same way. And so for light, it's easy. You can compute them in Minkowski. You find that going out is 2 over r, it's positive. Going in is minus 2 over r, and it's negative. Okay? Now the question, so there's the expanding and the contracting one in Minkowski. But the definition we have given here, they don't assume the signs. So now let's see if we can capture what a black hole is or what an horizon is by just looking at these two. So I'm going to give you the definition and then try to convince you. What is a trapping horizon? Well, if you send things in, they're going to contract. If you send things out, if you're outside the black hole, it's going to expand. If you're inside the black hole, everything is going to keep falling in, so it keeps contracting. What's the horizon? It's the place that is marginal. If you're outside, it expands. If you're inside, it contracts. Not contracting, not expanding, that's the horizon. Marginal. I'm going to skip these 3 things so we can discuss them later. I need to give you an example first. So I go to an example. Once we have the example, then we can discuss. And the example, been building it. No, it's Vaidia, yes.
So is the expansion a property of nearby null geodesics? Or
Yes,
can you?
no, it's not nearby geodesics. It's I see what you're saying. Yeah, you can think of it that way. You can say you can phrase it in terms of focusing and defocusing.
Okay.
No, you can say, suppose that I have a laser and I point it, so the laser starts with everything parallel.
Yeah.
And then I ask if the beam is going to be focused or defocused. Right. There's something on top of that here. I don't have a beam and asking the cross section of the beam. I have a sphere of a certain area. I shoot out radially. I follow that area following the beam, and I ask if the area changes, but one would say if the area is bigger, then it changes more. So I take the logarithmic derivative. Okay. And so it's not directly deviational geodesics. The deviational geodesics will be just for the cross section of it. Okay.
Why do we see a non-zero value for Minkowski spacetime? Wouldn't you
It's
expect?
exactly the point. Exactly the point. Minkowski has 0 curvature, so
Right.
there's no deviation on geodesic.
Right.
But there are geodesics going one way and going another way. And now what I'm doing is not to take one geodesic out or in, but a sphere, a shell.
I see.
And I ask the area of the shell.
Right.
Okay?
So the more the aerial radius, the more is the.
Yeah.
Okay, I see.
Yeah.
I see.
Okay, let me build the example because we have all the tools for having the example, and a lot of intuition comes from this example. And then the question is, can you write it more in more general cases where you don't assume spherical symmetry, where you don't have all these special cases that handles. So the idea metric, at this point, you should be familiar with it. If m equals 0, this is Minkowski. If m equals constant, this is Schwarzschild. We have m that can change in time because it's a black hole that forms and can grow. I'm interested in light rays going out and going in. You can compute them. Going in is just dr. Going out is this combination. How do you do it? You have to construct the double null coordinates for the area. Okay. Once you have that, then the area is just this function. You have to take derivatives. I worked it out. This is part of the homework, working this out. So I'm telling you the main steps. I want you to do this. And so the expansion going out is given by this function. The one going in is given by this function. The one going in is negative. No surprise. You shine light in, it goes in, and the area decreases. You shine light out, the area clearly increases in Minkowski. and also increases if you are outside the black hole. But if you are inside, it's where this thing changes sign. And so you are shining light out, but it's contracting. That's what a black hole does. And so where is the trapping horizon? That is the marginal surface where it doesn't expand and doesn't contract, is where this one is 0, which means that this has to be equal to this, which is a 2GM. You could have guessed it. I used the names of parameters so that it's really like Schwarzschild radius, but now it's not Schwarzschild radius in some abstract sense, it's in this concrete sense, even if M changes in time. Yes.
So what was the value of the outgoing expansion from Minkowski? Was it also 2 over or was it
Plus.
plus 2? So then the one below, didn't it reduce to 1 overall?
Did I miss? Yeah, I likely missed the 2. Good catch. Good catch. I missed the 2. I should fix this. Thank you. Thank you. You should have a 2. I think you're right. I think you're right. Yeah, good. Okay. So a remark. If M is constant, you can show that this horizon R equal to GM is null, like the event horizon we were discussing before. But now M can change. The black hole can grow. Non-trivial exercise show that if the black hole grows, then the trapping horizon is space-like. It grows, space-like. If the black hole evaporates, that is, it loses mass because of quantum effects, then it's time-like. Let's look at the case that we have spent time constructing. That is, there is no black hole, so we are in Minkowski, and then there's a shell of matter that arises, collapses, and forms the black hole, forms the singularity, and now we have to do the job of identifying these two notions, event horizon and trapping horizon. And I'm saying they are not the same. Well, let's do event horizon first. Event horizon is, I send in light rays, and they escape to infinity. I send in light rays, and they escape to infinity. I send in light rays, and they don't escape to infinity, they fall inside. What's the last light ray that can escape to infinity? Well, if I start from here, I really have to go this way, no? And it's going to be this one, the last ray. Eventually, it's going to come out this way. This is the last light ray. So if I start from the end, I know how to find it. It's this one. But if I start from this side, there's no way I can know where it is. Because after all, this shell came later. And so the last light ray, you don't know until the end. Okay? Let's follow it. So this one is 2GM, exactly like Schwarzschild. And then it goes this way. That means the thing that we were discussing last time, that is, if you are here, you are in Minkowski space, and then at some point a shell arises, and the horizon forms, but the event horizon is the light ray, so it has also this piece. And so you are inside the black hole and you didn't even know. Okay? Yes?
Then if you define this way, would you be saying that the horizon exists before there is black hole?
Exactly. The event horizon exists even before there is a black hole, but the only way to know is to wait the end of time. That's this weird construction that is mathematically powerful, but it doesn't have any immediate way of testing. So let's look now at the second notion, the trapping one. That one is local. Clear here, I'm in Minkowski space. If I send light out, it expands. If I send light in, it contracts. I can do it here. If I send light out, it expands. If I send light in, it contracts. There's no horizon. There's nothing happening here. There is an event horizon, but there's no trapping horizon. Let's go here. if I send light in, it contracts. If I send light out, it expands. And then you go here. If you send light in, it contracts. If you send light out, it also contracts. What is the boundary between the two? The marginal situation. The marginal is exactly here, where this way contracts and this way stays same area. Okay? So if you look at it, the event horizon formed down here in Minkowski and then expanded and then did this, while this trapping horizon naively seems that it just formed all at once when this shell went through. So now I have to split, I have to make it a little bit more complicated to make it more clear what is happening, because this shell, I'm making it really thin. Suppose that I give it some thickness. Okay? And then what you find is that if you give it some thickness, the horizon really does something like this. It forms here, it grows, it's space-like, and then it becomes this one. That is, there's a place inside here where at some point you shine light outside and it contracts. This thing of I shine light outside and it contracts, to convince yourself, you have to take this as a plot. You solve the geodesic equations and you say, well, I have initial conditions going in and initial conditions going out. Let's check what happens to the area. And as this is a plot in R, contracting area just means R going to smaller radii. If you do it in other coordinates, for instance, U and V, R of U and V is a complicated function. This is one more reason why this Eddington-Finkelstein plot, where here you put R, this one helps you check. You have two directions, going in and going out, and a separate notion of what contracting means, that is increasing R or decreasing R. I have to say it again. In Minkowski, increasing R and decreasing R and shooting light out and shooting light in, they coincide. This is for Minkowski. No? You have to distinguish the two notions. You have a laser, you can point out or you can point in. That's the notion of in and out. And then you can follow this beam and ask if the area increases or decreases. In Minkowski, the two things are related. But in a general space-time, it depends. Inside the black hole, you shine light out, and this shell contracts. Inside the black hole, everything contracts. Okay? Okay, I have one more plot here. This is a more diagram. So this was the shell that falls like this. Suppose that this is a star that collapses. A star that collapses, you have the star, it's static at the beginning, then it takes all its fuel and it collapses, it forms a black hole. The event horizon is null. The trapping horizon forms, grows, and then it becomes null. So outside here, where it's not accreting anymore, the two coincide. But before, this one forms this way. So can you say that this is a physical object, this trapping horizon? Well, it's moving space-like. So it's not an object either. It's a boundary region, but it's moving space-like. So it's not that it's an object that is moving. People would say it moves faster than the speed of light. That doesn't make any sense. It's just not an object. Okay? And we have done trapping horizon. Like this is the simplest case of trapping horizon. There's there's a comment now. So in mathematical relativity, event horizons, like the old theorems of Hawking and Penrose, they were all about event horizons. It's clear that you want to address this question of dynamically what happens, what are things that I can define without waiting the end of time. Trapping horizon is the starting point for defining all of these notions that are notions of dynamical horizon, where we identify properties of the horizon of the black hole that are dynamical, that can be defined locally or at least quasi-locally. So if you're interested in that direction, this is the first thing to look at, this notion of trapping horizon. There's a third notion I should mention that is old. It's important for another set of reasons that is called the killing horizon. This has to do with symmetries. So that's the next one that I have here in the list. And I don't want to go directly to that one. It's totally okay if we use the next 20 minutes to discuss, and next time we do killing horizons, because this one is a bit more heavy mathematically to do all the steps. There's a thing that I want to go back that I skipped, that is this figure here. We have discussed how to build the Penrose diagram for Minkowski, for a black hole that forms, for extended Schwarzschild, and then real black holes that form in nature often have a spin. And it's complicated to figure out what's the causal structure in that case. And it's important because these things are there in nature. So there's an object that is charged black holes with an electric charge that share many of the properties of rotating black holes, but they are spherically symmetric. And so if you want to learn properties of rotating black holes, a good intermediate exercise is charged black holes. Mathematically, one would have to cover that case anyway. Physically, it's less relevant. The black holes neutralize by themselves. Okay, so now what should I say? I should say, if you haven't seen the metric of a charged black hole, well, it's spherically symmetric. You see there's radius squared times spherical metric of a unit sphere, f of r, like in Schwarzschild. But there's an additional piece. They don't have just a mass, they also have a charge. And this is really a Coulombic term. You can think of this as if this is the mass and the mass has a Coulombic energy, then you should put also a Coulombic energy in the mass. Okay? And you see that here there's a minus, but here now there's a plus because it contributes a positive energy. And so when you look at this metric, if you just ask where the f of r changes sign, it changes sign in two places because this is a quadratic equation now. Yes.
How come the extra electric term is not also on? Why is one?
So the argument that I was giving is if you think of electric potential, it's 1 over r. Electric potential contributes to the mass. And so suppose that you here you put m plus electric potential, you would have a 1 over r times another 1 over r. You get the 1 over r squared.
Why does
You send m into m plus ev with v be q squared over r. And then you have 1 over r and another r here, and you get this r squared.
Why are you putting it in for mass?
Because I'm saying you can think of it really as 2gm, you can really think of it as the energy of the black hole, not just the energy that is bare mass plus the electric potential. And okay, so this is intuition. This is also a way of remembering when you're writing it. A better answer is you write a metric, you assume spherical symmetry, you have these two functions, then you look for solutions of Einstein equations, not in vacuum, in the presence of an electromagnetic field. You impose that the electromagnetic field is Coulombic, and so from the lines of the electric field, you can read the charge far away. From the things that we have done for mass, you can read the mass, and you read that this is the charge and this is the mass. And so I'm allowed to call it really charge because it behaves as charge, because this black hole has lines of the electric field exactly as if there was a point charge inside. Okay? And there is no point charge inside. No, like there's no point mass inside. Okay? Good. So now that you see this property, that this is a quadratic function, then you can ask, for Schwarzschild, you ask where this one goes to 0, and it's at r equal to gm. And now you can ask what are the two roots of this one, and you can solve it. It's a quadratic, it's easy. You find two roots, okay? Once you know these two roots, you can ask, where is the horizon? So you can ask, what is the event horizon? What is the trapping horizon? Before asking all those questions, there's a thing that is useful to do, that is, look at light rays, solve radial geodesics for light. Do this VR plot that we have learned how to do. Do this one. Do the complicated calculation of I shoot this way, I follow it, I see where it goes. Once you have done all of that, then you summarize everything that you have learned into a diagram. Okay? And so if you do that job, what you find the answer in books is this weird diagram here. And I want to make sure that we have the time to discuss this diagram. Because I don't know if you notice, when we did Schwarzschild, we did the extended Schwarzschild, this Kruskal-Sekeres extension, where there was an asymptotic region. Light could escape in this asymptotic region, and you could fall in. But there was also another unphysical asymptotic region on the other side, where you could fall in. So this is not different. It's a maximal extension in the same sense. If this charged black hole was formed by something and fell in, for instance, a shell that fell in, you have to throw away all of this. Don't believe it. That was just mathematics of a maximal extension. You would have to glue it to flat space. So that we throw away, that we don't have, that we have already learned. Okay? And so I really want you to look at this part here at the top. This part at the top, so forget this part. This part at the top, you can escape, or you can go in. You can ask what's the light ray, the last light ray that can escape. Well, it's this one. And so this one is the event horizon, these are plus. Then you can ask if this formed, if there's a notion of trapping horizon also. And yes, there's going to be a notion of trapping horizon. Things are untrapped out here, they are trapped inside here. And so there's a marginal surface. So this is also the trapping horizon. But now there's a new surface up here that we should ask about. And this one is not cut out by our cut and glue procedure. So if you fall in, the question is, where do you go? If you check, if you do the VR plot, you find that things that go in end up at a place. If I fall in first and you come up after me, we don't end up at different places at a given time, but we end up at different times. The singularity is time-like. You recall for Schwarzschild, the singularity was like this, and here it's like this. In fact, there's one on a side and one on the other. We have to make sense of all this. And if you take this seriously, you could go in and maneuver so that you don't end up in the singularity, because this thing it's periodic. You could attach the part that you see here. It's the same that you see here. So you could follow it and go out into another universe after. Do we believe this? I know it's a solution of the equation, but do we believe this? So I want that we discuss what is it that goes wrong. Because there's no doubt the maximal extension is you take this and then you glue one above the other, plenty of that. You could say, well, but in nature, I don't know of any charged black hole, but there are rotating ones. They have the same structure if you solve them. And so the question is, what does it feel like going in? Does it mean that you don't die if you are careful? Does it mean And this thinking green, that is this other place where things change sign, it means that here outgoing expands, here outgoing contracts, here outgoing expands again. Then it contracts, that is here, then it expands again. So in principle, I could go out somewhere else. Yes.
If you put initial conditions on a surface there, it doesn't cover anything which is like beyond this, right? So can we trust like our math if it tells us that it shouldn't go inside the singularity?
Can we predict? Like, if you are this space-time, once you are given the space-time, then you can follow a geodesic. You can say, I follow this geodesic. What's wrong with it? But if you want to build this space-time, let's be as concrete as possible. We have a code. Our code is give initial conditions, yeah, and evolve with our equations. Our equations, as you're saying, they evolve it this way, this way, this way, this way, this way. But you're not going to evolve past that. So can we really say that we can predict what happens here? Or are we just saying you could glue something, but we cannot predict if it's glued to that or to something else? So in a sense, this is a solution in the sense that you can glue something smoothly, yeah? But still, is there anything wrong that happens here? I agree that you cannot predict in the sense of, I can be more precise in what sense you cannot predict. Take this point here. How do I predict what happens here? I have to know everything in its past. Yeah. But part of its past is here. And I don't know what can come from a singularity. That's physics that I don't control. Okay? And so, am I allowed to believe anything of this part if it can be affected by quantum gravity? One more comments. Yes.
So the inner traffic horizon is when the outward light starts expanding again, correct?
Yeah, so outward here expands, outward here contracts, outward here expands, outward here contracts, and this one is this one. Yeah, I can do it this way. Plus, minus, which is this minus.
Except now we're like, okay, we expand in single layer.
Ah, I see. Would expand into the singularity if it was null, absolutely, but then I can be time-like and avoid the singularity. Yeah, good problem.
So if you take a point inside like the right square, the one below it, the one, yeah,
Maybe I should do this.
yeah, that one, yeah. If you take a point inside there, isn't the past of that point, doesn't that lead to that singularity? So you can't.
That's a good point. Shouldn't we already worried us here because we could we could get radiation from the singularity and die because the singularity. So that I address by saying, well, this black hole actually formed, and yeah, I should not trust this part. So I don't trust it for the past, but how about the future? Yeah. This was the same argument we used for Schwarzschild. No, we cut out from extended Schwarzschild the past singularity.
So then, what else?
Go ahead and then we come back.
Well, I was gonna say, just to double check, in terms of contraction or expanding, it's the
Yes.
upper triangle is just plus minus plus minus plus sign.
Yeah, let me try to make it precise. So maybe I should put numbers. maybe I should say, what's the way to put numbers? So let's say region 1, region 2, region 3, region 4, which is the same as region 4. And so I'm identifying this one with this one. And then here it's plus in the sense that outgoing expands. Here changes sign and it's minus. If I doing it right. Yeah, it looks good. Here changes sign again and it's plus. Here changes sign again and it's minus. And then it comes back plus. Every time you cross one of these marginal surfaces, it changes sign. I'm not saying anything weird. I'm saying you have something with two roots. And it goes from positive to negative to positive, I suppose. Then. Okay. So you had a follow-up.
I think I realized.
So let me raise the point again. I think I already convinced you that you should not believe anything that is before black hole forms. No, that's just flat space. There's no black hole here. The question is what happens after it has formed. So the first remark was, well, can we predict what happens? I don't know how to predict. Then there was another remark that is, suppose that I want to glue something here smoothly. Because one can say, well, you are right up to here, you know the solution of Einstein equations, so why don't you go just a little bit beyond by continuity, by analytical extension? And there's a second objection, that is, once you are on this side, then you would have to know what happens on this side. Well, I can still do it. I can say, well, I put also boundary conditions. Maybe boundary conditions that tell me that nothing is happening and here it's just quiet. I want you to identify there's one more problem. I don't think we have covered all the problems yet. There's one more problem. You haven't watched Interstellar. It's key in the
Is it that when you cross the first horizon, you can't stop going inwards, but then you cross over and suddenly you can follow a time trajectory?
I didn't catch it.
So the tangent along the t direction,
Yeah.
that goes from time-like to space-like to time-like.
Wait. Yeah, this line is always time-like.
Okay, I see.
Okay. The diagram is made so that
Right.
it's very easy to track
Right.
future pointing timeline.
Right.
Just goes up.
Right.
Where it's already straightened up everything. So the question I'm asking is there anything that goes wrong before crossing this line? After, we don't even know how to predict. The question is before. Do you die before? And then you don't have to. Is there there's something wrong here, but is there something wrong before we get there? There was this word like a Cauchy surface here. This thing here, people call it a Cauchy horizon now. The word horizon there is completely different from the horizons that we were referring to before, because it's just like where the Cauchy problem stops working. It happens to coincide also with these notions of inner horizon. Inner horizon is they have the same definition as before. You add one more line that is a further derivative. Check one more derivative. Okay, if you want to check the acceleration. Okay, maybe I should bring that up. It's not. Yes.
Sorry, this is. You just go back to the second, like an extra growth there.
Yeah. Yeah, theta is one derivative of logarithm of the area. this is derivative of theta. Yeah.
Changes.
Yeah. Yeah. I should bring up a point. We assumed spherical symmetry. Exactly spherical. Does that make sense? Well, yeah, I assume spherical symmetry and I ask about spherical symmetry. But if I perturb it just a little bit, does the perturbation remain small? Outside a black hole, you perturb a little bit a black hole, it radiates gravitational waves and turns out spherical. So even if I perturb it a lot, it's going to go back spherical. If I perturb it a little bit, this is just going to dilute. How about the interior? I perturb a black hole a little bit. Is the perturbation going to dilute inside or not? Or is going to focus? So this one is a solution, exact spherical symmetry, and the solution tells you that the curvature here doesn't explode. Yeah, yes, but yeah, it's okay. In fact, it's as large as here, more or less. You know, you could take a small charge and then it's essentially the same. However, suppose that you have a perturbation, you send in with your laser pointer, you send in something of a milliwatt, gets blue shifted. I'm passing here, and you kill me because this milliwatt get blue shifted. Any small perturbation, it gets blue shifted. If it's blue shifted, it's gonna back react. You thought that here this was just your charged black hole. But in fact, here, everything that you perturb is going to be larger and larger. In interstellar, before at the end, before it goes like wild, that would be this part. When the guy is falling, at some point it gets hit by things coming from the back. Is this radiation, back radiation, and the poetic license is that is not killed there. But you do get this scene, and Thorne describes it as, okay, you did the calculation of what you would get as you are falling, and then at some point, as you are falling in, you get radiation coming from your back that crosses you. It's this effect for a rotating black hole. Okay? And the argument that I'm giving you is a reasonable argument, but the hard mathematical problem is still open. There is no robust proof that perturbations make this place so unstable that actually your spacetime finishes here. Still at the level of a very reasonable conjecture with lots of support. So as it's not proved, you can put it in a problem. Okay. Yes. Yeah. Okay. So we have to check. We have to check just the outgoing one. And to check the outgoing one, don't forget that this one is a summary of something. So the exercise to do, which is one of the exercises in the homework, is you take that metric, you do this plot, either qualitatively or you put it in mathematics and you solve the differential equation numerically. So you go in, you come out. You go in, come out. And then here it's going to branch. And so you're going to find that you can go in and go to smaller radii, or go to larger radii and then again smaller radii. And then once you have that plot, then you summarize it into that diagram. And what you should find is this diagram, right? The reasonable part of this diagram, the one where you erase the part of the diagram. Yes.
You already mentioned that realistic black holes don't really carry a lot of charge, but can you also comment on the fact that you can't take the charge from arbitrarily large or fixed mass?
Yeah. Yeah, so suppose that you make this charge sufficiently large, then think of this charge as part of the mass. It would be like having a negative mass. If you do the geodesics, you will find that this singularity can be seen from outside. This diagram requires that this charge is smaller than this mass. Okay? And there are better arguments for this, but if you just start from just this metric, you see that there are two places where things go wrong. One is here if the charge is too large, and the other is when you look at these two solutions. If you don't have two real solutions, it means that really there are no horizons. It means that this parabola doesn't cross the axis. But if there are no horizons, it means that you can see the singularity. And this doesn't tell you that you cannot create these black holes. That's separate. Quick question, we are too close.
Yeah, when in the limiting case for them.
Yes.
Right.
Yes, that's correct. That's correct. That's the extreme case. Good, thank you.